Hello, Longhorns. Coming back to you with lesson number 10 on mechanical energy. We've been on the topic of energy, and keep in mind that energy is measured in joules. We talked about different types of energy, whether it's energy, radiant energy that's coming from the sun, or in this example, it'll be mechanical energy, which is when we combine kinetic and potential energy. Remember, kinetic energy is your energy of motion. Potential energy means that I'm still in one stationary position, but I'm saving or storing up that energy to be used later for something great. From lesson 10, chapter 5, we're in pages 169 through 173. We've talked about the word conservation before. So remember, conserve is pretty basic. Whatever you start with, you're going to end with. So the equal sign in all of your equations is very important. Make sure as you're going through your math step by step that number one, your guess method has been set up correctly. You want to identify all of your variables. Is it an initial or is it a final quantity? Number two, we want to make sure that we are multiplying or dividing or even adding and subtracting when we should. Pay attention to your negatives as well. All right? So, conservation of energy, we have two major distinctions, mechanical and non-mechanical. And for this discussion, we're on the mechanical side of things. That's where our kinetic and potential energy will fall. And there are other types, gravitational and elastic energy, that we'll talk about a little bit later. The big lesson of the day is energy is not created or destroyed. It simply changes forms. So, if I am moving a piece of metal and it's scraping along the ground, you'll notice after a particular amount of time that sparks will begin to fly. One way that we tend to lose energy or we have energy change forms is in the form of heat. When you see the capital ME, just like KE or PE, it's mechanical energy. What we start with, your initial, should be the same as what you end with. We'll also see this equation as well, and keep in the back of your mind that mechanical energy is equal to kinetic energy plus your potential energy. The roller coaster example is one that's going to come up quite a bit. And by now, you've probably figured out why roller coasters were selected as our topic or our project of the month. When it comes to roller coasters, remember from our last lesson that at the very top of your heel, you're going to have a high amount of potential energy, but a low amount of kinetic energy. On the day when you guys bring roller coasters to class, we're going to be calculating these areas, and we're also going to calculate the change in velocity. If you keep this principle in mind, your calculations will make a lot more sense. So at the very top, we have high potential energy, which means at the very bottom, we're going to have the lowest amount of potential energy, but the max amount of kinetic energy, because now you are truly in motion. The more hills we go over, the more changes in potential and kinetic energy we will see. So, let's try this problem. We have a student with a mass of 55 kilograms, starts from rest, and slides down a frictionless slide that is 3 meters high. What is the student's speed at the bottom of the slide? Now, on this particular problem, we're combining the kinetic energy equation, 1/2 mass velocity squared, to your potential energy, which includes mass multiplied by gravity multiplied by height. It all depends on what information you are given to start with. So let's set up our guess method. We have a student with a mass of 55 kilograms. Starts from rest, so that's your initial velocity, and slides down a frictionless slide that is 3 meters high. What is the student's speed at the bottom of the slide? So what I'm really asking you, not only about their V final, which is kind of what's in your mind, right? If you kind of look at it, we can also calculate potential energy. So we're going to do a little bit of both. So for our unknown, we want to figure out the speed at the bottom of the heel. And I'm also going to challenge you to calculate the potential energy that is at the bottom of this heel as well. All right? Now, potential energy for this calculation is very straightforward. So we'll start there. Equation for potential energy is PE equals mgh. For substitutions, I can look pretty quickly. Mass is in kilograms, velocity is in meters per second, and my height is in meters. So there are no substitutions to take place. If we want to calculate or go ahead and solve for our potential energy, we know that our mass is 55. For gravity, we're going to use our constant of 9.81. And of course, for height, we're going to use 3 meters. If you grab your calculators, making sure that we put everything in correctly, double check before you press enter, you will come up with 1,618.65 joules for your potential energy. Now, here's the other thing that we know. In this particular PowerPoint, you've also seen the following. Mechanical energy initial equals mechanical energy final. We've also learned that your kinetic energy, whatever it may be, will also be equal to your potential energy. Well, let's expand this equation out a little bit. Kinetic energy, the equation is 1/2 mv squared. And we just calculated our potential energy as 1,618.65 joules. Can I fill in the mass and the velocity? Well, we can find this velocity or the final velocity, right? So that equation we learned previously. I'll keep this side, and we're going to use this side for our additional calculations. When we are using or solving for V with kinetic energy, you have to be careful because of the square. In order to get rid of a square, remember that we will take the square roots. And this equation is one that will eventually kind of follow you. So we're looking right now for our final velocity moment. We're looking for the velocity at the bottom of the hill. Our equation that's going to be modified from this will be V equals the square root of 2 and that's how this is going to be rearranged. All right. Now, do we have everything that we need to plug into our equation? Well, we have our mass. We do have the initial velocity, but that's not quite what we're looking for. And we have our 2 times KE. But Dr. Kelly, how does that work? Well, we're going to plug in this number instead and see what we come out with. So we have V equals the square root of 2. Let's plug in this number. Divided by our mass. At this point, we can probably erase. Grab your calculators and let's simplify. The first thing I want to do is I want to go ahead and multiply my top number. So we have 2 times 1,618.65. Don't forget your square root. We're now going to divide our answer by 55. And last but not least, we'll go ahead and take the square root. And our final velocity comes out to be 7.47 meters per second. Now, one thing I will do as we're going back is keep in mind that we're talking about energy in general. So kinetic energy and potential energy should equal each other. So in your mind, you're doing this even though your equation was set up for kinetic energy. Your answer will still come out correct. Part 2 of this question. A student with the same mass, same student that's at rest and is 3 meters high. And they're going to ask you to also calculate the kinetic energy at the bottom. Depending on where you are, where it's located, and what's going on, you can calculate these all the same, keeping in mind that potential energy will always equal kinetic energy. We've actually answered this on our previous moment. Before you go, be sure to take a look in the textbook. The first page or first page and a half of every section normally contains most of the information that you will need to get through class. It also allows you to be familiar with the vocabulary. The goal is for you not to come in class never having heard the concepts or the terms that we're going to use that day. I'm open for your questions, whether in class or via email. I've also attached an additional lecture and some additional information from YouTube that you may find helpful. I'll see you guys in class.